My talk is titled The Rusting Cloud, and my name is Taylor Thomas, as was already introduced. So we're going to go ahead and I'm just going to give a quick introduction to myself here so we can so you can all know who I am. I also like to title this Why My Opinion Might Actually Matter. First off, I'm a Krustlet and Helm core maintainer, and we'll talk a little bit about Krustlet in a little bit. If you're at all in the cloud native or cloud software space, you've probably at least heard of Helm, and that's a package manager for Kubernetes. I've been doing Kubernetes and container things for a long time, so basically since the beginning of Docker and for quite a while with Kubernetes itself. I came to Rust by way of Go, which makes a lot of sense given my background. If you like to tweet out or ask me any questions or anything, or reach out on GitHub or Slack, you can see there, right there's my social media handle. I left my Twitter handle in the lower right-hand corner on all the slides in case you want to tweet about something or ask any questions or make fun of my slides, whatever you want to do. So if you can't tell, I'm pretty straightforward and frank with everything. I'm going to be completely honest during this talk about the various strengths and weaknesses of Rust in cloud development, but my opinion is still just my opinion. So keep that in mind. I have been doing this whole cloud native thing for a while, so hopefully that gives you some confidence that I'm not totally making this up for you. So yeah, that's just a little bit about who I am. Now let's go over what I'm going to talk about today. So first off, I'm going to give a brief intro into our projects and what WASM is, and then answer the question, well, but why? Why are we doing this? And then I'm going to talk about using Rust in cloud development with good, bad, and ugly. Now, I know we kind of have a mixed crowd here. Some are more Rust newbies, some are very experienced with Rust, some are experienced with cloud software, and some are not. So this is going to be focused on cloud software, and I'm going to be talking about some things that if you're very familiar with the language, you'll be like, oh yeah, I know that. But there might be some other things in here that you'll also be able to pick up on and learn some things. So this is meant to be the whole thing is meant to be a knowledge sharing presentation. So if there seems to be some consensus or there's questions coming in to dive into another topic more in depth, or if people want to skip something, I'm completely fine with that. I don't have to cover every single thing I've written down here. I want to make sure that we can cover the things that are of interest to people here. And then at the end, we're also going to have a little bit that's kind of a tongue-in-cheek joke about it being a cage fight between Rust and Go. That's a question that people ask us a lot. So I threw that in there as a little bonus content so we can cover it about. So yeah, the Rust and cloud development section, when we get there, I'm going to use the kind of classic good, bad, and ugly overview of what we found in Rust. It's very useful, things to keep an eye out for, and so on. So let's go ahead and intro the projects that we have. And first, to understand all the projects that I'm going to kind of use as a backdrop here, I need to mention what WebAssembly is. So WebAssembly is known as WASM. And if you're not familiar with WASM, WASM is a compiled binary that can be run in a browser through JavaScript, except that's its main use right now. And so it allows you to have the speed of compiled code while still running in something like a browser environment. However, WebAssembly is not just for the web. There's a new specification called WASI, so the WebAssembly System Interface, that gives a set of ways of interacting with a host system, no matter what operating system it is. And so one thing to be aware of is it's relatively new. It's only been around for about 2 or 3 years, and it's not all the way fleshed out yet, but it's on its way there. And when I say not very fleshed out, what I'm meaning is that's very, very true. There's plenty of things missing, like there's not a full networking specification yet. And there's actually like, for example, we released an experimental HTTP support project that's meant for WASM, and it's just meant to bridge some of these gaps that are in there right now. And so WASI is a way that means I can now take these WebAssembly binaries and run them on every single kind of system. And I'll talk more about those advantages in a sec. So here are the projects. Now these projects are what I'm going to be drawing from as I go over the different parts of Rust. And now all of these are real world projects that are where there's a fairly large code base involved with various servers, clients, code machinery, all the things you'd expect from a project that deals with distributed systems or cloud software. These are all relatively recent projects from us, and they all fall into that like cloud native bucket in general. So we'll be using a lot of examples from Krustlet and then a few from these other projects as well. So I want to give each of them kind of a proper introduction. Now, all of these projects are open source. So if you're interested, feel free to contribute code, bug reports, whatever it might be through these projects. I'm not really going to give a super detailed intro to the WASI HTTP project, but I might mention it in context of other things. And I just wanted to drop the link there so that people can take a look at it. So these are all under, and I guess that I just realized I forgot to introduce that. So Deus Labs is my team at Microsoft. I work for Microsoft, but my team works primarily all in the open source space with these kinds of technologies. So that's where that's from. So first off, Krustlet. Now that first line, that first bullet looks ugly, but that explains where the name comes from. It stands for Kubernetes Rust Kubelet. If you're not familiar with Kubernetes, the kubelet is the thing that runs on a node inside of a Kubernetes cluster. So its primary purpose is to run WASM modules. So modules are the name of the compiled binaries. So it runs these WASM modules within Kubernetes. Now we have inside of this a idea of providers. Now this comes from another project called Virtual Kubelet. We stole this kind of idea of having a provider, meaning that you can implement any sort of thing that you want to. We've heard some people are trying to do some stuff with systemd. We've had people try to re-implement container support. You can implement anything you want with these providers. Now we've created a few that are just mainly targeted at WebAssembly, so WASM targets, and Rust. Now the reason why I say Rust here is because there's some really good reasons that we're going to talk about of why you would want Rust to write a Kubernetes thing. And especially like a provider. So you don't have to remember all these concepts, but that's like, you might see that some of that terminology and things as you look around. And it basically allows people to write whatever sort of kubelet they want within Rust. Now, inside of the project, there's actually 3 crates that we export. One of them is Kubelet, which is the actual thing that runs the kubelet component. We have OCI distribution, which is a partial Open Containers Initiative, like the Open Containers Initiative interfaces that implementation. And then we have a project called Crater with a link to what that is, but it's a fully featured compile time checked state machine in Rust for building Kubernetes operators and other things, which is used inside of the Krustlet project. Next up, we have Bindle. So Bindle is an aggregate object storage system. The easiest way to explain this is a silverware drawer, a flatware drawer. So if you have you generally have a drawer that contains your forks, your spoons, your knives, and all the little fancy things you need for more fancy dinner, or if you're doing also you generally have so many different utensils in there. And so for breakfast, you might only need something like a spoon. But for a fancy dinner, you might need a spoon, fork, a knife, and then like a chilled salad fork or something else. Now, all of these things are related. Most people generally don't have a separate drawer for every type of utensil. And so the idea was that a lot of things in the cloud native space, they don't allow you to put related objects all together. And so in taking this example of the silverware drawer, if I want to select a certain number of WebAssembly modules that I want to use depending on what kind of system I'm on and how much processing power I have, this allows me to select the specific set of binaries that you need for a project. So the first use case this was we created it for was enabling our WASM and WASI projects. The idea being that we can pull, like I said, those modules and then use them the way we want them to. However, there could be some really other interesting use cases for this. If it is interesting to you, reach out to us on GitHub. But it also turns out we kind of stumbled on this, that it could be useful for securing software supply chains. Bindle is strongly typed and versioned. So there's basically a manifest of what objects. It's called an invoice in Bindle. Each of these things are signed by the person who creates it and the server that hosts it. And it must have an exact specific Semver version. So this is just an interesting project that I'll show some code from as well, but is tied into this WebAssembly module. We also have this WAGI project, or WAGI project. So it stands for WebAssembly Gateway Interface. And yes, you read that right. It is a CGI implementation that basically allows WASI modules to act as HTTP handlers. So you're able to compile it, whatever your code's doing down to WebAssembly, and then have it act as a handler for a specific HTTP endpoint. So this was just another way we went around enabling HTTP for WASI. And Bindle can be used with Waggy to pull the proper modules down, or you can upload modules. We're still building that project out, but that's another one that we have. So we get to this, but why? Like, why did we write all these things in Rust? Why did we choose WASM? Why did we integrate this with Kubernetes? Why did we even mess around with cloud stuff at all? Isn't Rust a systems programming language? Those are the questions that people often ask. So let's dive into why. So first off, let's talk about the WASM and WASI side of things. I like to title this, but wait, I already have containers. Why do I need something else? So first off, these two are fairly self-explanatory. So there's more security. WASM modules run in a completely sandboxed environment. You have to explicitly grant permission for them to be able to access anything. Density, we're talking about an order of magnitude smaller in size. So you can have if you have a well-crafted Docker image, you're talking probably 20 megs, 10 megs, depending on what kind of thing you have in there. If you've built your containers right, you can generally have, or built your WASM modules right, you can generally have them between 1 to 5 megs, depending on what they're doing, which is much smaller. And also the things needed to run them, you don't need a full Docker runtime. You don't need any of that. You just have to have a WASI compatible runtime that can run these things. So it's a lot easier to run these in other places and to pack them more tightly. Now, just a point here, this isn't meant to completely supplant Docker, but because there's certain workloads that are never going to be worth porting to WASM, even if everything was in place. But this is where we get to it is actually run everywhere to an extent. We like to say, if you've been in the cloud space at all, and you've used Docker, we like to say, oh, well, Docker is work anywhere. And it really isn't. If we're just being honest with ourselves, it's a Linux technology. Now there are Windows containers, but they're very different from a Linux container. They aren't the same thing. If you have an Nginx container that's running somewhere on a Linux server, you cannot run that exact same container on Windows that isn't also running a Linux VM. So it's not actually run everywhere. And you contrast that with WebAssembly, and it's closer to this dream of having a universal binary. So I can compile a WebAssembly module on my Mac that I have right here, and it will run on my Windows machine out there. It will run on a Linux server in the cloud. It'll run on a Raspberry Pi. It's going to run everywhere. And that is very, very powerful and helpful. So between the size shrinking and that, it's super useful. And like I said, you have this overhead of Docker and other container runtimes that makes it really hard to run on embedded devices. And there's some interesting use cases that people have started to try around using WebAssembly on embedded devices. So that's one of the big reasons we actually have Krustlet, is to enable those kind of people to try that out. So the next big thing here is Rust and WASM are great friends. So if you've toyed around with WebAssembly at all, you'll see it really quickly. But a lot of the tooling in the WASI space is actually written in Rust, and it has a built-in. You can easily use Rust up to add a target for building or compiling to a WebAssembly target. And so because of that like built-in support, it made it a natural choice for building WebAssembly-centric applications like Krustlet or Waggy in that language. So another thing that answers kind of the why here is about Kubernetes in the cloud. So for many people, especially those late adopters in terms of companies, that Kubernetes is the cloud. Now, I don't necessarily agree with that. I don't think that should be the thing, but whether I like that or not, Kubernetes and containers have become synonymous with running applications in the cloud. Most people who have migrated to or are currently migrating to the cloud have interacted with Kubernetes in some way. So we created Krustlet as a way to allow people to try WebAssembly in a familiar environment. So you can start to see how all this adds up. We have Rust, which has great support for WebAssembly, and then we're tying this into into the cloud. And Krustlet Kubernetes was the good place to give people a familiar place to try these things out. But also, we discovered Rust is a really great fit for working with Kubernetes and other cloud applications with similar APIs. And that's where I'll mention this. And so I know we're getting here, and I'm sure some of you are asking, like, oh my gosh, Taylor, you are at a Rust meetup and you're just barely getting to Rust. And I get that, but all of this stuff is really important to understand how we use Rust in cloud development. And what its strengths are and what its weaknesses are. So here's just kind of an overview of the things that we've seen in Rust. These are the high-level reasons why we chose Rust. So the first one is safety, which is one of the oft-touted features of Rust. To quote one of my coworkers when we were kind of compiling some of the information around this, he literally sent me in all caps, "No damn null pointers," because safety is required, and unsafety, as I'll call it, is explicitly called out with the unsafe keyword. I can easily grep through code and find where all of my unsafe calls are. And so I know exactly where something like a null pointer or memory issue can happen because of Rust's strict ownership rules that keep everything inside of it very safe. The rest of these are pretty self-explanatory, I think. I already explained the WASM support, and most of us who've used the developer tooling in Rust, such as Cargo, know like the developer experience truly is top class. Now, the extensibility one might have you scratching your head a bit, and so I'll explain more about that in the next section. But basically, Rust as a language makes it very, very easy to design flexible and extensible APIs, which isn't necessarily true for all other languages that are common in the cloud software space. We're talking Go and Python and some of those other those languages. It's a lot harder to design flexible and extensible APIs. So were there any questions yet that I should be aware of before I continue on?
Yes, there have been questions, but your colleague, Radu, I think is his name, already answered them. So he took over the job.
Thanks, Radu. Let's go ahead and dive into the whole Rust in cloud development. So this is all Rust in context of cloud development. These are answering the questions, or what are the experiences we've had? What have we liked? What was hard for us? What should you watch out for when you're starting your own new project? And so these are all based on real experiences and code from our projects. Now that these projects are a little bit bigger than just kind of toy projects that we do on the side. Now, some of what I'm going to talk about here can be found in the blog post I have linked on this slide. This is a blog post I wrote about a month ago, but we're going to be diving into more details and other things that's just in that blog post. And you'll be able to ask me any follow-up questions here at the end. So let's just dive right in. So let's start off with the good. So this is not just about the good things. This is about like how things went with our projects and how we felt Rust really showed its power. So first off, let's talk about traits. We have absolutely loved the trait system in Rust. If you're coming into building your first cloud software project, you'll immediately see how useful and flexible and expressive it is. In particular, we really love the conversion and reference traits. So this is like as ref, from, try from, deref, from string, all those kind of types. And those are the great examples of why we consider traits to be better than most other interface style types that we've encountered in other languages, because the type itself doesn't have to implement an interface to be used as another type. Deref is a really interesting one to us because you can basically use that object as the underlying type. If you're not familiar with that, that's exactly what happens when you use the owned string type. Most of the methods are actually implemented on the underlying borrowed string, so ampersand, str. Most of them are implemented on that and not on the owned string type, but you're able to access both methods because of the deref trait. Here is an example from our Bindle. Sorry, this is Bindle. I was about to say Krustlet, and that wasn't right. So this is from Bindle. And it's just a simple example of how this is super helpful. So right now we have this type that implements try into, and we have a custom ID type to make sure that the ID fits the strict requirements we have for a Bindle. And so what this allows you to is to pass in any type of string or anything that can be parsed as an ID into this. and it implements a certain type of error type coming back out. So while the function signature looks more complicated than some other languages that you might be used to from the cloud space, it ends up being extremely easy to use as a consumer, because you can pass, I think it's about 8 types when I tried to calculate it all out to this function, and all of them work properly. Now, the other thing that's really nice, and you can see this here, is we have the idea of traits can declare associated types. You can still have generics even in an interface context. So right here you see error. So there I was able to specify a type that implements the error trait in Rust. And so because those were all tied together, I was still able to use this very generic try into interface with my own custom error type. And that's very, very useful. The other thing to think about this is if you're familiar with a lot of cloud APIs, and especially Kubernetes, you have types that are all very similar, but you can perform different actions on them. And so in Go, which most of the Kubernetes libraries are written in, you have a separate interface for each kind of type of API type. In Rust, there's actually just a single generic type and client that can access any Kubernetes style objects, which is so useful and cleans up code so well. The other good thing we found is enums. They are very, very helpful, especially we found in error handling. Enums changed how most of us think about errors, because Rust enums are not just single values, right? They can carry associated data with them. And each variant can have a different data structure. They're kind of like discriminated unions from other languages. And you can work with these different cases using pattern matching. And so because they're also a full-blown type, you can then also implement methods on that type or traits for that type. So the big value here is that you don't have to bundle a bunch of possible cases into a single type to pass into or return from a function. And working with the cases is safe because the compiler tells you if you haven't matched everything, and also there's no need for optional fields here that might only apply to certain cases. And so this allows for code, or it encourages, I should say, code that processes enums to be have very clear regular layouts, and it makes for some very beautiful code and generic. So right here you can see that I have an example error type. This is kind of a pared down error type from Bindle. And I'm able to have totally different data associated with each type. And then when I go down below, I'm able to unwrap and do things with that data very, very well. This is very helpful in really anything that involves like an API or network call, because there can be so many things that fail. There can be something with the network that fails. There can be something with the service is offline. There could be something where you have an invalid request, or the request, and it can tell you exactly why, if the request needs more data. All these things are very common interactions, and Rust has easily been the best way to handle those kind of situations in our experience with things like enums and other types of error handling. I mean, you can see too, because enums can also contain generics. This is one from Krustlet that allows us to specify a very specific state type when you're transitioning from one state to the next. And that is that generic type added on to all the power of the enum is very, very helpful and very flexible. So the other thing we've run into that is extremely useful inside of at least Kubernetes, and I think a lot of different cloud applications, is macros. So writing macros can be a little bit finicky if you haven't written one before, but let's just use this example to walk through what we were able to do here, which is useful for cloud software. So in Kubernetes, there's this idea of something called a custom resource. It's an arbitrary resource that you can tell Kubernetes to handle as one of its normal API types. And so people use this to extend on top of Kubernetes. But inside of other languages, you have to import full other libraries or other things to either compile the right code, or it has to be generated code. With a macro, this is created at runtime using the macro as it compiles. So this custom resource derive allows you to go through and specify just a few arguments saying, here's what it should be. And then the data that we actually care about inside of our Rust program, and then derive the whole implementation for it automatically. And you also see in there the very classic SERDI, serialize and deserialize, which to us is just absolute magic compared to many other languages, because you can derive these implementations, and then anything that implements the SERDI data model, you end up being able to then, just because we've derived these, be able to serialize it to any type you want, YAML, TOML, JSON. There's more types than that. Those are kind of the big ones we see in the cloud native field. We're also able to derive a JSON schema for this. And all of this is done. So now, instead of having lines and lines and lines of code or generated code we have to handle, this is all just a derived block that, if we include all this formatting and stuff to make it look nice, is maybe 10 lines of code. And that is extremely clean code and easy to kind of figure out what's going on. So that's something that, as you come into Rust, either as a newbie or as someone doing cloud software, like, I think we find macros useful anywhere in Rust, but there is a distinct joy in using them in the cloud space because of how flexible they are and what they do for you. So just keep that in mind as well.
Taylor, can I interrupt you for a second?
Yeah.
You asked me to relay questions, and I wasn't fast enough, to be honest. There is a question concerning enums. Yeah. Matthias is asking whether there is any specific reason why you didn't use a library for error handling. He thinks that this error would really reduce the code needed. Any thoughts on that?
Good question. So actually, I paired that off of here just to keep it simpler. This is using this error underneath the hood. So we have derives and things under here we have the derive error, and then we also have the error type, the error tag on each enum variant. And so this actually takes it and prints it out. The handle error was also a simplified case of what it was doing. We're actually doing some like logging and other things inside of the handle error function, but the example was simplified so it wouldn't completely take up the whole slide or two slides. So yes, that's a good point, and good. Thank you for reminding me to bring that up. There's some error handling libraries that are meant to work with enums like this and clean up a lot of the code. And that's what we actually use. It's called this error, and it allows you to derive and then specify error messages for each enum type, which is exactly what we do inside of our errors, especially inside of Bindle, because Bindle is implementing an API and also a client. Krustlet's a little bit different because we have to handle Kubernetes errors, which are a little bit more loosey-goosey. So good question. Were there any others?
Currently not. I think that's the only one which was unanswered. So
okay. Sweet. Feel
free to go on.
Okay, now another good thing to be aware of here, this is on our very high on our list of impressive Rust features, is a whole amazing set of mapping, unwrapping, and iteration tools. The built-in result and option types, combined with all the mapping methods that are associated, and like if let or let variable equal match, and then being able to match on something, makes it really easy to handle errors or missing data in a very simple and easy to read format as well. And it also nudges you towards clean and readable error handling patterns, such as the try operator, so the question mark, which is really helpful for people who are new to the language. After coming from various types of error handling, including exceptions, and then the way Go does it, coming here and seeing that wonderful syntactic sugar of the try operator was so nice. It's very helpful to people new to the language. And I know that when I've been helping people come into these projects and start working on it, they're able to read and understand what's going on with error handling very, very easily. So this block right here is a little gnarly, but this kind of shows there's the whole suite of like chainable filters, maps, splitting, zipping methods, similar to how LINQ and functional programming languages handle collections, along with the all-powerful collect method. So this is 20 lines of code that does a whole ton of work for us and shows off most of these features. So what's going on in this code block is we're trying to find what data that's called a parcel in Bindle, which doesn't matter here, but how many data buckets we're missing inside of a Bindle. And so we're able to go through all of the things we expect and then iterate over them and then map them into futures, which then we can take all those futures that check if they exist on disk, collect, like wait on all of them, and then join them back all together. So basically this is a fan out and fan in 20 lines. So that is very, very helpful, especially when you're doing some of the code that happens a lot inside of cloud computing, and not just cloud computing, but anywhere really. But a lot of what we have to do is kind of massage data from one source to be able to use it. And these chainable filtering and mapping and all that just makes it so easy to massage that data and get it into the format we need to be able to either return or to use that data that we're getting. So like I said, the block's still gnarly, but we do a lot here in a very small amount of space. Now, we also have inside of the good is this dependency management. So we love Cargo. I'm not going to spend too much time on it because I'm hoping people are at least somewhat familiar with Cargo. But the fact that you can have conditional compilation and you can patch in dependencies from other places and only include parts of the code that you need with features. These two examples kind of show that. So we have a CLI that's using clap that instead of having people pull in clap and everything with it, they can opt into it using a feature. And you can see above how we're doing that in various dependencies. We're able to select only specific features of some generated API objects. We can add additional features in or make them optional so that we only enable them when we need it. We can also work on a crate locally, but when it gets pushed with the right version. That's like the OCI distribution line there, which is all quite useful. And the other thing that I can't say enough about is the Rust community. So the Rust community is absolutely amazing. It's not only just inclusive, but it's also very responsive and helpful for newcomers. A recent example of this is we were having a deadlock issue in Krustlet with Tokyo, and all the core maintainers of Krustlet had just been like working on it for a week going, what is going on? And so we asked a question. Well, I went over and asked a question on the Tokyo Discord channel, and one of the core maintainers responded very nicely in less than 5 minutes. And then not only did they provide some very helpful and useful information to me to be able to troubleshoot, they also came in and went to the PR and dropped in a few more suggestions. And this isn't the only time I've seen that kind of behavior. It's something I see all the time in the Rust community. And you'll never be made to feel like you're asking some sort of stupid question. People will always respond with kindness here. And so I really, really enjoy the Rust community. So you'll always find people out there, even if you're doing something completely crazy, which is a lot of the stuff we've done around Kubernetes, and people will still be out there to help you out. So let's kind of go over some of the things that we consider like the bad and ugly. I'm going to kind of gloss over some of these. I don't want to spend too long, but let's just talk about some of the things you need to be aware of that we've kind of run into with our projects. So first off is docs and clarity. So we've noticed an interesting pattern in a lot of our crate in lots of different crates and their documentation. That's something to be aware of as you consume and as you write your own crates. So docs are actually sometimes very unclear what is happening in the actual code. So they describe functionality well, but we generally have to go digging through the code to figure out whether it's an actual fully like zero cost abstraction, if there's possible side effects to what we're doing. So like we don't know sometimes if something is copying under the hood, or does the file handle get flushed when I call this function? And a lot of those things aren't very well documented. And because of this emphasis on zero cost abstractions, we just kind of assume sometimes we have to handle it or don't handle it. And so it's not documented very well. So this happened to us in Krustlet with Stack Overflows on Windows, which I couldn't put here. It's too large, but we're basically Krustlet runs a whole bunch of futures that are all running different tasks for the system to work properly. And what happened is when we started trying to get it to work on Windows, it would just Stack Overflow. And we're like, well, what's going on here? Well, it turned out in our newbie Rust brains, we forgot to think about that when we were selecting on all these futures, it said that it needed to be pinned. And so everything was pinned to the stack, which is kind of the default of how when you pin something, it works in Rust. But it turns out we didn't necessarily need to do that. And we didn't understand what kind of abstractions or things were going on there because there was no cost. And so we were just pinning to the stack and it was taking up way too much stack space. So once we figured that out, we were able to pin it to the heap because we were fine with using things from the heap. And And so that's just something to keep aware of. Now, up here in the slide is an example that's related but slightly different. So as users, when we're trying to find out how we can customize behavior by implementing a trait, we end up jumping through like a million different functions, looking at all the trait bounds before we can figure out what we need to implement. And oftentimes these traits are in other crates. So this is an example from the absolutely wonderful Tonic crate, which allows you to use gRPC connections across and use gRPC files to generate the proper code for it as well. But you look here, there's this make connection URI, and then you have two associated types that are related to it that need to be send and static, but like what are those types? What has to be implemented? And so you would click through to make connection. It has its own things, but it also has to implement like async read and async write. And you just go down this big chain. And so there's like 3 or 4 distinct bounds, 2 with different traits. It turned out that all that was actually needed was the code right below, which is super simple. And we found that in the examples directory. So something to be aware of coming into this is if something looks confusing, try to make sure you go look at the examples directory of the project, because they might have something there. But if you're somebody who's writing a crate, make sure you link to an example for something that's this easy, because it turned out to be super simple. But as someone who was looking through this, trying to figure out which traits and things I needed to implement the first time, it was very difficult for a first-time Rust person figuring this out. So just make sure that you document and link. And please note that right here, these are the old docs that we saw. They actually, since I've written this and we've talked about it, they actually added in a link to the example of how to implement something for this function. Another thing to be aware of that we've run into in a lot of our projects is that in the Rust ecosystem, for at least the cloud computing and like HTTP things, there's still a lot of missing features. So one thing that we ran into recently is we found out there isn't much support for multi-part content types in HTTP requests, except for form data. So this is not like a complaint against any specific developer of the crate. We think this is more due to Rust still being newly popular and its primary use case being systems programming. But in this cloud space and really application developers in general, there's just some gaps in the functionalities. We'll talk about the async space in just a second, but there's a lot of things with HTTP that aren't completely there. You have different HTTP library choices instead of 1 or 2 de facto ones or built-in support. So up here is an example of one of the worst ones we had to deal with. So Unix domain sockets on Windows. If you didn't know, you can actually do like Linux sockets on Windows machines, which is something we had to do for Krustlet. Now, that's all built in the standard library for Unix, and it's not in the standard library for a good reason, because Rust supports back to something like Windows 8, and this wasn't added until Windows 10. But there's no maintained crates to do this in an async way. So this is not a problem with Rust itself. I'm not complaining about Rust itself or the people who write these things, but if you look at all these unholy things we had to do with the code, just don't ask me what that reinterpret cast is doing. You don't want to know. But we had to go implement basically all the reading and clear read ready and add read ready and all that stuff in from someone else's crate and kind of copy and do all this stuff because it wasn't there. So you're going to run into gaps, and it's a perfect place where you can contribute back to the community if you find that interesting. Another thing is that people like to complain about the learning curve of Rust. Now, my personal opinion on this is that Rust does have a bit of a logarithmic learning curve, like what's showed here, that there's a very steep initial learning period of about a month, but it levels out pretty quickly. And in our team's experience, after about a month, a developer is just as productive as they were previously. Doesn't mean you're still not still learning. It just means that you're able to be as productive as you were before. But now that we've been releasing several different crates and things, there's a few more bumps in the road to be aware of, in the bumps in the learning curve, I should say, as you start writing your own crates and doing things. One of them is that there's a learning curve around designing APIs, particularly when working with an API that uses generics or trait bounds to make it easy for public consumption. There's a certain amount of knowledge we've had to pick up by trial and error about how to use them in a way that doesn't end up being messy for us or messy for the consumer. And I've refactored my code several times at this point to fix these kind of messes. You just have to look at the Git history of Krustlet to see all the fixing we've done there with some of those. And this is where if you have experiences and things to create any training material or documentation, this could help ease that part of the learning curve, because it was something we didn't really anticipate coming in, but now that we've done a lot of it, that is definitely part of the learning curve that not many people mention. You just have to learn how to design APIs and design things well inside of Rust. So let's finish up with the ugly. I didn't want to, this isn't like, there's only one topic here, and it's really about async and async runtimes. But to be really clear, I want to emphasize, I'm not trying to rag on any of the async runtimes or contributors. In fact, like I said in that story before, they're an absolute joy to work with. And also, I think yesterday or today, they're just releasing a new async working group that we've actually contributed an initial story to kind of capture how we can improve the async story, especially for application developers. But I do want to point out that in the cloud software space, this is the part that is the most rough for people. And honestly, it really is impressive what the core team and runtimes like Tokyo have done within the constraints of Rust. And you really can't complain when your concurrent code is guaranteed by the compiler to be completely safe and correct. It's saved us from plenty of bugs already. But with that said, let's talk about it. So one of the things to be aware of is that there are competing and incompatible runtimes. So there's multiple runtimes that are available. Tokyo and Async Standard are kind of the two major ones. And you kind of have lock-in once you choose a runtime. Now that makes sense from a systems engineering perspective that you have multiple runtimes, but from a cloud software perspective, it is quite frustrating because you come from Go where you can just say go run, and it just runs. You don't have, or you just can shove it off to have it run asynchronously. And so having different runtimes is a little bit different than most other languages. And I know that you can make it possible to run across multiple runtimes, but it's difficult. And if anything in the stack only runs on a different runtime than the one you're using, you have to basically bake in some sort of shim or thing to wrap it to be able to work. It keeps getting better, but it's just, you have to be aware of it. Something to note here is that the core team has been stabilizing a lot of APIs into the standard library. Like the stream one should be landing soon. And we have the futures one that allows standardizing easier and reduces that lock-in, but just be aware of it. The other thing that we've noted is there's some ugly code and nested futures problems. So here on the left is something from Waggy. You can, if you're familiar with Rust, you'll see why all these clones and moves and stuff are needed for memory safety purposes. But, and part of this is also how the hyper API works. But you move, clone, move, async, move, clone, move, like 3 or 4 times all in one thing to make this work, which it's just kind of, it reads poorly. It's kind of hard to follow along why you need to do it. And you kind of like, we had to play around with this for an hour to figure out which moves and which clones and which things we needed to make it meet the FN mute and all the other stuff that's going on. So it can add to some weird, ugly code issues. But on the right is something that's probably the one that can be a little bit worse when it comes with the ugly code and nested futures. So this code right here is actually what caused the Stack Overflow before we boxed it properly. But right here, we have to like call each individual thing, fuse it, box it, pass it into a select, handle each of the things. And this is only part of it. There's like another set of tasks that have to run, and then we have to wait on all of them. So we end up with very deeply nested futures as these things go along, which can really like bloat your stack size and give you some problems there. So just be aware that that's there, and we're always around to help if you run into that issue. And then last in this section is cruft and bloat. And this happens with async. What we've noticed is that it adds a lot of cruft and or bloats your code with all the different incantations and things you have to do to make it all compile. When you compare this to other languages like Go in the cloud space, it's kind of a hassle in comparison, and it's something you need to be prepared to deal with. So on this left one, this is us implementing async read for an async type. If I had $1 for every time I had to re-implement async read, async write, or a stream for a type, when I just end up forwarding that call down the call chain, I'd be a rich man. And this particular example kills me because this is already an async type in every way, but to be able to wrap it with the proper things, I had to go re-implement async read on top. And as a developer, I really don't want to have to do that. And it's this whole chunk of code that really, in the end, is not doing much for me. On the one on the right, the other thing we run into is that there's opaque types littered everywhere. because everything is like hidden behind the future trait or a stream trait, everything returns an impl future and impl stream. So you can't store it on a struct for later use. You can also see this happen with like your docs when you have an async trait, because you have to wrap it in the async trait macro, and it creates a very, very ugly doc. So it just adds cruft and bloat that you're probably not used to. I mean, like I said, the benefits outweigh these problems, but you have to be aware of it. Okay, finish up for the bonus round here, Rust versus Go. So interestingly, something that we found at least very interesting is that one of the most common questions we get when we talk about Krustlet with people is, well, why didn't you use Go? And how does Rust stack up against Go? I personally don't think it's as much of a flame war as people present it to be, but there's some important quick comparisons here that I want to talk about. First off, what do we miss from Go? What we miss from Go is an ease of concurrent task scheduling. Like I mentioned, all I have to do is say Go and the function name, and it just runs asynchronously or concurrently, not necessarily asynchronously. There's also a batteries included standard library, including HTTP support. I know there's good arguments for not having like an HTTP thing built into the standard library, but it sure is helpful in Go. It's also easier to onboard new developers. It's much easier to get started on a Go project than a Rust project if you haven't done either one of them. Now, what do we not miss about Go? Dependency management. And I don't want to sound like a broken record if people have ever followed me on Twitter or read any of my other blog posts, but Go dependency management is just not good. You can ask any of the Helm maintainers on my team or any of them at all. Cargo just makes our lives in dependency management so much easier. So as someone who's developed really large projects against the Kubernetes libraries and API, it's an absolute nightmare to upgrade or add any library dependency because they all have different versioning schemes and specific hashes and branches. The other thing is if error equals nil. Error handling in Rust is much better. We really like the idea of an error as just a value that you get in Go, but Rust enforces it rather than Go's approach of just hoping that the programmer does the right thing. And then there's no generics, or even with the new generics that are coming in, it's just, like I mentioned with the trait system, we love it. It's much better than anything Go offers. Go's governance model is also being controlled completely by one company, and that's led to various community problems and project issues. Rust has a very open community model that we've talked about, the Rust Foundation, and it's not singularly controlled. There's no collections or iterator function, and there's no safety. And this isn't unique to Go, but it's important when we compare these two. It's really easy to end up with a null pointer in Go. And like I said, in Rust, it's impossible without unsafe. So to summarize that, when do we use each one? When do we recommend to use each one? So for Go, small, quick projects, a true microservice, a very small microservices, or super deep integration with very specific cloud tooling. For Rust, we recommend it for larger projects anytime you need a flexible API or if there's safety or security requirements. So the summary of that is that Go is a great tool for the small projects and microservices that need to be written quickly or with ease, but we don't really recommend it for new projects or large projects. Large projects quickly become bloated due to that error handling, lack of mapping and iteration tools, generic support, bad dependency management. That's not to say there aren't large projects that do well with Go. We have plenty on our team that do it as well, but the overall experience leaves a lot to be desired. So anyway, that is a very quick overview of all the different things we've learned here. So I better leave some good time for questions or anything that people want to ask.